Hey.
Oh, yeah, nice to meet you. Yeah, I haven't talked to the department yet, but I'll talk to them after this.
Should I stay?
Yeah, you can stay.
Thank you.
So they walked in. Is this your first class? What's our second one? Who's our last
Sometimes you like
I'm serious, during the break, I had like specific facts that just could not be. Can I wake up around? I didn't get this number. I got 1 to 2. How to do it. The first one. My eye. This one, like the whenever I tie or cerebral eye, right? There was a form where it was like, you got to do that or something. Yeah. Right, yeah, and then you next is just nice.
see them together. I can just
Right, mine.
negative for. It was like I was sitting under when I got cold. But I didn't, you know, I saw.
I just no else. I do. I know this one's pretty another one. Well, this is a lesson on I see this. Yeah. It's for Not knowing from running. Then just now.
You must be doing finals at your first time.
No, I still remember that.
I always remember you were
Crazy tests.
Yeah, still next.
What's the, for settings? Literally. So. Settings.
But I also haven't tried electric belts on. I was doing it. Because this is my first one. And later on, once the added the one.
There's salt.
No, because depending on the year, but. This,
Oh,
this,
yeah.
this is the only one we did. That one with HN and Delta. Yeah. That was. Yeah, and I have my notes. Exactly. I saw the note that it's, you know, yeah, I had a lot. Yeah, thank you. Such feasible. So you could, yeah, okay, yeah, yeah. Thank you. But it's in the just like one over. But if you do this. One over. I that. Oh, maybe I did the injunction as well.
Something about the.
I was composing.
It might be just.
I started last night.
Or maybe it's a version.
I had one more thing to do. I had a. Yeah, I got home and I hadn't smashed it. I started like one sentence, I was like. No, but I will do it today. No, no.
Like not bad.
Yeah. My, probably. Yeah. We're good. No, we're gonna be so you can see, like, in the basement, 34 or whatever. I think. You see, one point, I think we're in. We're gonna be there at 7. I'm assuming we're in there. ongoing conference. It's honest reason.
It was easier to remember the Yeah, I don't thought of that word. I don't see your final. Oh, it's just. That's how I feel about color. You have to do. Yeah. It's true.
On the plane. Have a layer just showing the day. Sure. Maybe. Baker. Chill. I'll give the open up.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Doing good, and
Good, good. Thanks for asking. All right, we're on day 2. So today is our first real lecture, I guess. You know, Tuesday we kind of just introduced the class. Okay, so plan for today is we're going to be going over first order ordinary differential equations. So you may have seen this before in Math 250B. If you don't remember, it's okay. We're going to learn it again. And we're going to do some examples for that today. Okay. All right. So quick announcement before we begin. I did post your first problem set. So I posted that yesterday afternoon. So that is homework 1. So the due date for that is actually coming up pretty quick. It's going to be due next Thursday, January 30th. And basically that homework set is just practice for first order ODE. So basically everything we covered today. I'm hoping to finish up first order ODEs today. So after today, you hopefully should have everything that you need to do that homework. All right. Any questions I can answer before we get started for today? I have to like peek around because I can't see this past this monitor. Short. Okay. All right. So let's go ahead and get started. By the way, this is kind of the normal kind of lecture style that I do. I might have mentioned on Tuesday, but usually you'll see me with kind of like my iPad and Apple. Well, this is not a real Apple Pencil, it's a cheaper version of it here, and then I'll be writing up here as a pseudo kind of whiteboard. So you probably won't see any slides for the rest of the class. Okay, so topic for today is first order ordinary differential equations. All right, so quite a mouthful, quite a mindset too. I almost didn't fit it all. Okay, so 308, you know, we're going to spend a lot of this class talking about differential equations, and differential equations are, you know, probably right after calculus is probably the most important, mathematical topic for you to know as engineers. You could even say that differential equations might be kind of a weird second cousin to calculus because it involves derivatives, but they are very important. Okay. So let's define differential equations first. Okay. A differential equation is basically just some kind of equation that relates a certain variable along with its derivatives in some kind of mathematical way. Okay. So, hopefully everyone's familiar with the concept of a derivative. So derivative is nothing more than just the rate of change of a certain variable. Okay. Now, when we talk differential equations, we have to kind of make the distinction between different kinds of variables, right? And so on the one hand, we have what's called the independent variables. Okay. So these are variables that don't depend on any other variables in the equation, hence they're named independent. Okay. So for this class, for the most part, our independent variables will, I'm mostly going to use x, which is to denote some kind of distance. Okay. So those will be functions in space or t, and t here stands for time. Okay. So in other words, we're going to be looking at differential equations where our variable changes with either space or time, and that probably covers 99.9% of cases in engineering. Okay. The other type of variable that we need to know here are the dependent variables. Okay. So the dependent variables are going to be the ones where their value depends on the values of the independent variables. So for example, right? One case you're going to see a lot in this class is, we're going to have y, where y is going to denote some kind of position of a of something. Okay. And y is going to be a function of t. Okay? So what this is telling us here is that y is a function that depends on t that describes the position of an object as it goes through time. Okay. And so in this kind of simple example here, time is our independent variable. That is the one that doesn't depend on anything. And position depends on time. Okay. All right. So when you have a function like this that depends on an independent variable, you can also form its derivatives, right? So if we know that y depends on t, then we can have dy dt. Okay. So dy dt is the rate of change of position with respect to time. Okay. So of course, the rate of change of position does have a name that, that a lot of people are familiar with. Rate of change of position is velocity. And oftentimes you see this in, in applied mathematics or engineering science, so that, rate of change is kind of a mouthful. And so instead of saying rate of change of position or rate of change of position, we say things like velocity and acceleration, just so they're, shorter to say and really more simple. Okay. Now, some other notation that you'll see, I'll try to write out, the full derivative, just because that's how I prefer to write it down. But some other ways to denote a derivative is to use an apostrophe. Okay. So y prime in this case can also denote the derivative. Or sometimes you'll see a dot above the head too. Okay. So all of these will denote the derivative of y. I usually don't like to use these shorthand notations because it doesn't tell you what the independent variable is. I like to use the full dy dt because I tell you that y is the dependent variable, t is the independent variable. But sometimes it's been more convenient to use this shorthand. Okay. Okay. Any questions on this so far? Okay, good. All right. So a differential equation. So now that we know what a function is, what a dependent variable is, and its derivatives, a differential equation will take these two things and then kind of combine them together into one equation. Okay. Okay. So for instance, a differential equation may look like the following. We have dy dt, which is the derivative of y, plus, maybe 5y is equal to 0. Okay. All right, so we have a single equation here that relates the derivative of y together with the actual variable y together in one equation. So this y, that's part of the derivative, and this y are one in the same. Okay. It's just that in the first term, y appears as a derivative. In the second term, y appears as just itself. Okay. All right, so the first, I would say maybe 40% of this class is going to be based on these differential equations. Okay, so now what is an ordinary differential equation? So that's probably a term that you've heard a lot. So ordinary differential equation is another one of those mouthful type of terms. So you'll see me shorten that a lot. Okay. So you're going to see me use the term ODE a lot in this class. So ODE stands for ordinary differential equations. Okay. And ODE is simply a differential equation with just one dependent variable and one independent variable. For the most part, ordinary differential equations, that's kind of where most math classes stop, at least at the undergraduate level. Kind of the other form of a differential equation is called a PDE, or partial differential equation. And so in those cases, you can have more than one. Usually, it's more than one independent variable, but you can actually have more than one dependent variable as well. And a lot of very famous equations in engineering are PDEs. So things like the heat equation, Navier-Stokes equation for fluid mechanics, conservation of mass, and so. But those are really scary to solve. So we're not going to solve the PDEs. We're going to focus just on. Okay. Okay, so how do you solve an ordinary differential equation, or what does a solution look like? Now, I think, before you take a course in differential equations, when someone tells you to solve this equation, whether it be in calculus or in algebra, a lot of times you're used to solving for just one variable, just one expression, right? And ODE is a little bit different because the solution to an ordinary differential equation is actually another function. I think that's probably one of the more difficult things that's kind of wrap your head around, is that the solution to this function is another function. Okay. And the reason for that is that the solution to the ODE is a function of how the dependent variable depends on the independent variable. Let's see. All right, so the first thing, to really learn about this, about differential equations, is to at least verify that a function is a solution. Okay. So to check if a function is a solution to a given ODE, you're going to do basically the same thing that you normally do in algebra. You just take your solution and you plug it back into the original problem. So let's do a couple of examples to kind of see what that looks like. Okay, so first example, let's look at this differential equation. So let's say we have x times dy dx is equal to minus y. Okay. So here we can see y is our dependent variable, because we have a derivative in y, and x in this case is our independent variable. Okay. So that's our differential equation. So let's verify that the function y of x is equal to 3 over x. Okay. Let's verify if this is a solution to the differential equation. Okay. So to verify that if this is a solution to our original differential equation, we're just going to take this guy and plug it back into there. So basically, everywhere that you see y, you're going to plug this guy in. Okay. So y appears twice in our equation here. So we have y in its derivative and y on the right-hand side. So we're going to take this solution, plug it in here, and we're going to plug it in here. Okay, so let's go ahead and do that. So we have x times derivative with respect to x of y, which is 3 over x, is equal to minus 3 over x. Okay, so to finish evaluating this, we do need to evaluate this derivative. Okay. So we have 3 over x let me go ahead and put that in another form that makes it a little bit easier for us to take the derivative. So 3 over x is the same thing as 3 times x raised to the -1 power. Okay. So when you raise something to a negative exponent, it just goes into the denominator. So we can go, we can reverse that as well. So if we see something in the denominator, that's the same thing as, raising it to the -1 power. Okay. And so if we take the derivative of this, we can use our handy dandy power rule. And so power rule basically states that, we take whatever's in the exponent, which is the -1. We multiply that out in front. Okay. And then we subtract 1 from the exponent. Okay. And so when we evaluate this derivative, we get a -1 times 3, which is a -3. Okay. And then we end up with x raised to the -2 power. Okay. We did -1, which was the original exponent, -1, we get -2. And of course, we can put this back in fractional form. So this is going to be equal to -3 divided by x squared. Okay, so let's go ahead and plug this in, and then we'll see that this solution is actually verified. Okay, so if we plug that back in, we have x times our derivative, and so the derivative that we just computed was -3 over x squared. And then the right-hand side, we just have a -3 over x. The left-hand side, we can simplify a little bit because we have an x in the numerator and x squared in the denominator. So this x, it's always difficult with x because you try to put an x through it and it just lines up perfectly with that x. Okay. So that x is going to cancel out with one of the x's in the denominator. And so what we get in the end is -3 over x is equal to -3 over x. We have the same thing on both sides, and so this is proven. So this shows us that y is equal to 3 over x is indeed a solution. Solution verified. Any questions on that example there? Cool. All right, let's do one more example. This one's a little bit more complicated, although not that much. Okay, so let's consider this differential equation. So let's have dy dx is equal to y plus e to the x. Okay. So once again, let's verify. Let's verify the function y of x is equal to x plus 4 times e to the x. Okay. Let's verify if this is a solution. Okay, so once again, we're going to take this function here and plug it in everywhere we see y. Okay. So on the left-hand side, we have derivative d dx, quantity. I'm going to go ahead and distribute this e to the x to both terms here. So we have x times e to the x plus 4 e to the x. And then on the right-hand side, we have y, which is x e to the x plus 4 e to the x plus e to the x. Okay. So when we evaluate that derivative, it should be the same thing as the right-hand side. Okay. So let's go ahead and evaluate this derivative. a little bit of a longer term here. It's not just one function. But we can take advantage of the fact that a derivative is a linear operator. And so whenever we see plus sign, that means we can break up the derivative in between those. Okay. That means we have d dx of x e to the x plus d dx of 4 e to the x. Okay. I'm going to go ahead and simplify that right-hand side, because the right-hand side we have, well, x e to the x is kind of its own independent term. But we have 4 e to the x plus e to the x. We add those together, we get 5 e to the x. Okay. So now we just have to evaluate the derivatives on the left-hand side. Okay. Okay, let's start with the easy one. Let's start with the second derivative. Okay. So we have derivative of 4 e to the x. So 4 in this case is just a scalar constant, and so it actually doesn't participate in the derivative, so we can actually factor that out. And so we have derivative of e to the x. E to the x is our favorite derivative to take because derivative of e to the x is just e to the x. Okay. So derivative of this is just 4 e to the x. Good. Now let's take derivative of that first term there. So we have x times e to the x. So we have the function of x multiplied by another function of x. We try to take the derivative of this, right? This is a very common application of our product rule. Okay. So product rule means we're going to take derivative of the first term multiplied by the second term plus derivative of the second term multiplied by the first term. Okay. Where this x here, that's term number 1. And this one is term number 2. Okay. Okay, so when we apply product rule to this, we have derivative of x is just 1. So we have 1 times e to the x plus derivative of the second, which is e to the x. Derivative of e to the x is just e to the x. Okay. Multiplied by x. All right, so if we add these all together, we have e to the x plus 4 e to the x. That's going to combine together, become 5 e to the x plus x e to the x. That one has no common term, so that one just comes down on its own. Okay. And if we compare this to the right-hand side here, okay. Their order is swapped, just because I'm an idiot, but you can see that both sides are equal to each other because addition is commutative. Okay. And so we say these two are the same. So our solution is verified. All right, any questions on this example here? Hopefully it was a good quick refresher of product rule. So we'll be doing chain rule, product rule, quotient rule. Even I don't really use that all that much. A lot of times you can just put things into product rule form, but good to know. That's kind of why I did this example. Okay, all right. So this is the first thing that I cover in 308. Every time I teach 308 is how to check your answers by plugging in. But it's also the thing that literally almost no one does in class. And so, always a good idea to check your answers, especially on the exam. So if you look at the homeworks, you'll see that I've actually given you the final solutions for all the homework problems. And so, of course, on the homework, you can check that way. But on the exams, if you're not sure about your answer to a differential equation, just plug it back in. And so, the perfect way to check your answer is already kind of built into the problem, which is kind of a nice thing about this subject. Okay, so that's how we check if a solution is a solution to a differential equation. Now, how do we actually go about finding that solution? of course, you know, this is where we're going to spend the bulk of our time. All right, so for first order ODEs, there's actually not that many techniques that are out there. There are two main techniques that we're going to go over. Okay. So the first technique that we're going to go over is for it's called separation of variables. Separation of variables is a little gimmicky, you know, it doesn't always quite work out, especially with equations that come from engineering. But it's I guess it's a little bit of a simpler one, a little bit easier to learn. Separation of variables only works if your differential equation is separable. And we'll talk about what that means in a second. Okay. The second technique, which is probably the one that's more useful and more common in engineering, is what's called integrating factor. That's probably the one you're going to use most of the time when you're talking about engineering equations. It's not that common that you get a separable equation, but you know, having a linear equation that works with integrating factor is quite common. Okay. So let's start with separation of variables. Okay. So the idea with separation of variables is that, you know, if you look at all of our differential equations so far, they all involve some equal sign, right? And the equal sign, you can kind of think of it as kind of dividing the equation into a left-hand side and a right-hand side. Okay. And so in separation of variables, the idea is to manipulate the equation in such a way such that on one side of the equal sign, you have everything that only contains y, or your dependent variable, and on the other side, you have everything that is just the independent variable. Okay. So a lot of times, you know, when you solve a problem with separation of variables, the separation may not be immediately apparent, and so you kind of have to massage it a little bit mathematically in order to, you know, get the variables into the right places. But the idea is that if you can do this, then finding the solution, you just simply kind of integrate both sides. You just kind of integrate them straight on. So, you know, that's kind of a nice benefit. So mathematically, so I have to choose some symbols here for the dependent variable. Typically, you're going to see me use y for the dependent variable, and either x or t for the independent variable. Okay. So mathematically, it's going to look like this, and so we have g of y. Okay. where g of y here, this is some expression that only contains y. Okay. Multiplied by the derivative dy dx, okay? This is equal to f of x. For this f of x here, this is an expression that only contains x. Okay. So if you can manipulate your differential equation to be in this form, then it's separate. Right? I know it's a little bit hard to visualize with kind of just the generic symbols here, but I think once we do a couple of examples, I think you'll start to get it. Okay. Okay. And so if you can do this, what you can do is you can just integrate the left-hand side with respect to y, integrate the right-hand side with respect to x, and then, you know, you just kind of you carry out those integrals and then you'll have your solution. So, you know, the hard part with separation of variables is actually in the algebra. And so just manipulating the equation to get in this form. And sometimes, you know, a lot of times if you don't know if it's separable, just like trying out different things in the algebra to get it to a separation state, that's the hard part. But then once you get it in this state, it's pretty straightforward. Okay. All right, any questions on this before we do a couple examples? Okay, all right, so let's do a couple of examples. Okay, so first example that we're going to do, let's do dy dx is equal to 1 plus y squared. And we're going to solve this one using separation of variables. Okay. So, you know, normally I won't, you know, you won't be given this. You won't be given, you know, right from the beginning what technique to use. I'm giving it to you this time just because, well, you know, we just finished talking about it. So, you know, sometimes the hard part is determining what method should you use. Okay, but since we know this is separation of variables, we know that we can kind of work on it from that perspective. Okay. Okay, so let's try to get this equation into a form like this above. Okay, so we want to take everything with y and then move it over to the left-hand side. Okay, and we want to actually do it without creating some new terms. So one thing that you might say is that, okay, we have y squared on the right-hand side. Let's subtract y squared from both sides, right? So we have y squared minus y squared on the right, minus y squared on the left, right? We move the y squared over there, but that's not quite the form that we have above here, okay? Because if you look at the equation that you have above, right, we have this form g of y, but that g of y, that entirety is multiplied by our derivative dy dx, okay? Okay. So if you take this expression, and don't write this down, this is incorrect, okay? And so if we take this expression and we minus y squared on both sides, okay? So you have dy dx minus y squared is equal to 1, okay? On first glance, you know, you might think like, okay, you know, this is good. So we move the y squared to the left-hand side. So y squared is no longer on the right. So we should be, you know, good to go. Well, in this case, this y squared is subtracted from the derivative. It's not multiplied, right? So we actually can't use separation of variables with the equation in this state. So we need to manipulate this equation in a way so that, we have an expression multiplied by dy dx, okay? So let's do this instead. Instead of subtracting y squared from both sides, let's divide this entire equation, so both sides, by 1 plus y squared. Okay. And so if we do that, we have 1 divided by 1 plus y squared multiplied by dy dx. Okay. It's equal to. And on the right-hand side, we have 1 plus y squared divided by 1 plus y squared. That's just going to give us 1. Okay. All right. So this expression that we have here now, this does satisfy our requirements for separation of variables, but because we have this entire expression here, which is 1 over 1 plus y squared, okay? The entire expression is multiplied by dy dx. And so now we can actually take this and we can integrate it. Okay. Okay. So to integrate this, I'm going to show you kind of or at least this logically the way that it works in my mind. Although I know if you talk to a mathematician, this is mathematical war crimes here. But what I'm going to do is I'm going to multiply both sides by dx. Okay, so I'm going to bring the dx over to that side. Because in reality, you can't do this. You can't take apart a derivative like this. I'm aware, in math Nazis, but this is what makes sense to me. So on the left-hand side, we have 1 over 1 plus y squared dy. And on the right side, we have dx. Okay. So I've decomposed the derivative, but technically you're not supposed to do this, but it's fine. Okay. So if we integrate this, notice how on the left-hand side, we are integrating with respect to y. On the right-hand side, we're integrating with respect to x. Okay. Let's do the right-hand side first. That one's a little bit easier to do. Okay. And so if we integrate that, we get x. Okay. Because we essentially just have integral of 1. So integral of 1 dx is just x. Okay. And then the left-hand side, we have integral of 1 over 1 plus y squared. So this is one of those, I guess, integrals you look up in a table. And so the integral of this is tan inverse of y. If you don't have that memorized, it's okay. This is just one of those just weird cases. I only picked this example because it had the y squared. I wanted to subtract it, but this is not something I expect you to memorize or know. Okay? It's one of those weird derivatives. Okay. But there's actually one more thing we have to do before we actually move on to the next step. So if you notice, these two integrals that we perform here are indefinite integrals. And what that means is that, they don't have an upper and lower bound. And so whenever we perform indefinite integrals, we always have to add an arbitrary constant to our solution. So these are indefinite integrals. Spell that incorrectly. Okay. Whenever you perform indefinite integrals, your solution is only ever valid up to an arbitrary constant. So you want to make sure that you add that to your solution. Okay. So let's go ahead and finish this up. So we want to solve this equation for y. Y is there. It's just kind of implicitly defined within the tangent. So let's go ahead and take the tangent of both sides. And so by taking the tangent of both sides, that's going to cancel out with the inverse tangent. And so on the left-hand side, we're simply left with y. And on the right-hand side, we have tan of x plus c. And that right there is our solution. All right, any questions on how we got that result there? My roommate in college was a mathematician, so he always used to poke fun at my engineering work. So you're not doing real math. I'm like, I am doing real math. We're both doing real math. It's not a secret club. Everyone can do math. Okay. So before I move on to the next example, I do want to point out one characteristic of this solution here. Okay. Notice how our solution still has arbitrary constant c. Okay. So this solution is only valid up to this arbitrary constant. So whenever our solution has an arbitrary constant like that, what we say is that this solution is our general solution. Sometimes there's more than one constant, but for now we're just going to stick. Now, a lot of times a general solution isn't, that's not satisfying enough for an engineering problem. And so, oftentimes we want to find the full solution. Okay. So a full solution is one where a value of the arbitrary constant is specified. So instead of just being a generic C, we actually put a number in there, like 1, 2, 3, 4. Okay. But we can't just specify anything that we want. So usually to get a full solution, you have to apply what's called an initial condition or a boundary condition. Okay. An initial condition or a boundary condition is a additional kind of requirement or a constraint on the solution based on one particular point or one particular location. Okay. The next example will have a boundary condition, so you'll kind of see what that is. Okay. But I did want to make that distinction. So, usually when you solve differential equations, the first thing that you're going to find is the general solution. And then after you find the general solution, then you're going to apply an initial condition or a boundary condition to solve for the arbitrary constant or constants when we get to second order. Okay, so let's do another example. This one's also kind of fairly simple, but this one has well, technically it's an initial condition, I guess. Okay. So in this example, let's say we have dy dx is equal to minus 2 xy. Okay. So once again, we're going to solve this equation using separation of variables. But this time we're also given an initial condition where our initial condition y when x is equal to 0 is equal to 1.8. So when we get to the end of the this of the problem, and we get our general solution, we're gonna plug this in to solve for our arbitrary constant. Okay. But first, before we do that, we need our general solution. So let's go ahead and separate the variables, right? So this one should be pretty straightforward. So we have a, well, our derivative on the left-hand side is by itself, so dy dx. And on the right-hand side, we have minus 2xy, okay? So to get y, so you know, our goal here is to get y onto the left-hand side. Let's divide both sides by y. And so on the left-hand side, we have 1 over y dy dx is equal to minus 2x, okay? And so with that one simple step, we've separated the variables. So now that we've separated the variables, we can now integrate with a little bit of war crime. So let's take the dx, put it over on that side. So we have 1 over y dy is equal to minus 2x dx. Okay. Integrate. We have integral of 1 over y dy. And that's going to be integral of 1 over y is natural log of y is equal to integral of minus 2x. That is a minus x squared. And then we have our arbitrary constants. By the way, you know, I know we're performing indefinite integrals on both sides of the equation here. So technically, you know, we need to add arbitrary constants to both sides. But since it's arbitrary at this point, you know, we haven't specified a value for it. You can kind of combine both constants on one side just to make things a bit easier for yourself. So that's why I only have the constant on the right-hand side. Okay. So let's go ahead and simplify this. So let's solve for y. And so we need to cancel out the natural logarithm on the left-hand side. So the way to cancel out the natural logarithm is to raise both sides to the power of e. Okay. So we have e to the ln of y. And on the right-hand side, we have e to the minus x squared plus c. Okay. That e is going to cancel out the ln. And so on the left-hand side, we have y of x. Okay. And on the right-hand side, we have e to the minus x squared plus c. Okay. All of that being in the exponent. We can simplify this a bit because remember, we haven't specified a value for c yet. Right? Remember, when you have you know, addition in the exponent, all that means that you're multiplying those two terms together. So this is e to the minus x squared multiplied by e to the c. Okay. All I did was just kind of separate them into two terms there. Okay. The reason I do this is because, you know, just to make our life a little bit simpler, so we're not solving for c. Okay, because we know c is an arbitrary constant that we haven't specified the value yet. We haven't applied the initial condition. E is a constant. It's a very annoying, irrational constant, but it's still a constant. And so to make our lives easier, let's replace this. The entire expression, e to the c. Let's replace this with another constant a. Okay. So we have y of x is equal to a e to the minus x squared. Okay. So now we're solving for that a instead of, you know, e to the c, trying to find out that c. So we, you know, we kind of saved ourselves from having to do it anymore. Okay. And so now we arrive here at our general solution. So a solution that is, you know, valid up until that arbitrary constant. Okay. Any questions on how we got to this this part here? All right. So last thing before we get on to integrating factors is let's go ahead and apply our initial condition. So our initial condition states that y, when x is equal to 0, is equal to 1.8. Okay. Right, so that's what was given to us at the beginning of the problem. So let's use this initial condition right here to solve for the value of a. Okay. So to use this initial condition, we're going to take the value of x in the parentheses here and actually plug that into our general solution. So we're going to plug x equals 0. We're going to plug x is equal to 0 into our general solution here. Okay. So we have y of 0 is equal to a times e. Instead of minus x squared, we have minus 0 squared. Okay. Right. 0 squared is just 0. Minus 0 is just 0. And we know e to the 0 is just 1. Okay. So that entire thing there just becomes a. And then based on our initial condition, right, we know that when we plug x is equal to 0 into our solution here, that's going to give us 1.8. Okay. So now that we plugged in our initial condition, it doesn't always work out so nicely like this. This just kind of worked out just almost perfectly. But we get our solution here that a is equal to 1.8. Okay. So our full solution or our final solution is y of x is equal to 1.8 e to the minus x squared. All right, any questions on how we use that initial condition there? All right, and so that's separation of variables. So again, that's usually the first method that most people learn. Okay. So I don't think we'll get through all of the integrating factor today. We only have about 20 more minutes, but I at least want to introduce the concept to you. And I think probably on Tuesday we'll probably start class with an example. Okay. So let's talk about how to solve these equations with integrating factor. Okay. Okay. So integrating factor is a technique that will only work on what's called linear ODEs. Of course, that begs the question of, what does it mean for an ODE to be linear? A linear ODE is one where the dependent variable and all of its derivatives only appear in the equation in the first order, or I say first polynomial order. Okay. linear is actually quite a general term in mathematics. It's just to indicate any time that, you know, something is just not raised to an order greater than 1. Okay, so let me give you kind of the general form for this. So the general form for a first order linear equation, and again, I'm using y and x here, is equal to, so if dy dx plus p of x times y is equal to r of x. Okay. So fairly simple equation here, but there's kind of a lot to unpack. Okay. All right, first, let's check if this equation is linear. So let's look at the dependent variable. So dependent variable is y. Okay. So we have two y terms here. So we have first we have its derivative, so we have dy dx, and then we have y by itself, or technically it's multiplied by p of x. Okay. And so if you look at the polynomial order for both of these terms, right? They're not squared, they're not cubed, they're not square rooted, right? All of these are raised to the first power. Okay. So there's no, you know, y squared, there's no dy dx, raised to the 1/2, okay? So if you have, you know, y squared 1/2, you know, derivative to the 1/2 power, that would be a nonlinear equation. So this wouldn't be on the table. Okay. Another thing you have to kind of be careful of is that, you know, you can actually multiply the dependent variable by its derivative, and it still will count as a nonlinear term. Okay? So let's say you have y times dy dx. Okay. This right here is actually nonlinear. Okay? So if you see this, okay, if you see something like that, then you have a nonlinear equation that you have to solve it with separation variables. Okay. Same thing for like 1 over y dy dx, or 1 over 1 plus y squared dy dx, right? In all of these situations, you have some function of y multiplied by the derivative of y. So all of these are non. Okay. The first one there, actually 1 over 1 plus y squared, that's super non. You have y squared, and you're multiplying that by dy dx. So, yeah, that's impossible. Okay. So that's the first thing to highlight here, is that every time you see y or its derivative, it's in the linear mode. Okay. The other thing to notice here is that if you look at the other terms here, so you have p of x and r of x. Okay. P of x and r of x here are functions of only the independent variable. Okay. So it's okay to have functions of the independent variable there, but not of the dependent variable. The dependent variable should only appear in the first one. Okay. Okay. So a little bit more terminology here. There are special cases for when r of x is 0 and r of x is not 0. Okay. So r of x here is the expression on the right-hand side of the equal sign. Basically anything that's not multiplied by y or its derivatives. Okay. So when r of x is equal to 0, we say that the equation is homogeneous. Okay. When r of x is not equal to 0. Okay. So in other words, when we actually have something for r of x, we say the equation is non-homogeneous. It seems kind of a silly thing to give a term to, but it actually does have, you know, implications with in engineering. Which, you know, I think we'll get to next. Because first thing is, you know, we have to actually, you know, we have to actually figure out how to solve a situation like this. Okay, so what makes this a little bit different than before, especially in the presence of a non-homogeneous term, is, you know, we usually are not able to separate these terms, okay? Mostly just because we have the addition. Okay? So we have to take kind of a different approach. But there are some things of separation of variables that we actually really liked, right? And so the one thing that we actually really liked about separation of variables is the fact that, you know, eventually we were able to get it to a point where we can just simply integrate both sides of the equation. Okay. So that's really nice. And so because if we can do that, then that's, you know, a very straightforward way to solve for our dependent variable. Okay. So we want to be able to get to that, but because our equation has a different form here, we have to use a different technique. Okay, so let's do a very kind of short derivation here. I think we can finish that in the next 10 minutes here. Okay. All right, so let's take our equation here. So you have dy dx plus p of x y is equal to r of x. Okay. I'm going to assume for a second we have a non-homogeneous term. Okay. So let's take this equation and let's multiply it by another function. So let's take our problem that's already difficult and make it even more difficult, right? Usually a good idea. So I'm going to take this entire expression here and multiply it by another function, which we'll call mu of x. Okay. And it's special, so we use a Greek letter instead of you know, a normal letter. Okay, so let's distribute that. So I'm going to distribute that mu of x throughout the entire equation here. We have mu of x multiplied by dy dx plus mu of x, p of x, y is equal to mu of x, r of x. Okay. So all I did there was I just took our new function here, mu of x, and just distributed all through the other side, on both sides. It's just that there's three terms in this equation here, so it kind of looks like a mess. Okay. So remember, you know, we want to get this into a form where we can just simply integrate both sides, right? So I'm going to propose this, and it's going to look like I'm just pulling this form out of my ass, which I kind of am. But I'll kind of show you kind of the motivation for it in a second. Okay? So what if we turn the left-hand side let's utilize our new function here. What if we turn the left-hand side into this? We have d dx of y of x multiplied by mu of x. Okay. So we have the derivative of the product of two functions of the independent variable. Okay. Right. And why would we do that? Or where did this come from? Okay. Let me show you. So let's take this expression here and let's expand it using product rule. Okay. That's why we reviewed it earlier today. Okay. And so when we expand this using product rule, we have dy dx plus, or dy dx multiplied by mu of x, so derivative of the first multiplied by the second, plus derivative of the second d mu dx multiplied by y of x. Okay. If you look at this, and you look at this, right? They're actually pretty similar, right? So in both those cases, we have two terms. We have two terms separated by a plus sign. One term has a dy dx and a mu of x. So actually the first term in both of these are exactly identical. Okay. So this term and this term, identical, right? Just again, I swapped the order because I'm an idiot, but you know, they're the same, trust me. Okay. Second terms look similar, but not quite the same. So second terms, we have y on both, so that's kind of a good start, right? So we have y up top, y on the bottom. Okay. The difference, of course, is in the interpretation of this terms, right? So you have d mu dx on the bottom, and on top we have mu of x, p of x. Okay. But what if we took these two things and we set them equal to each other, right? Because right now we haven't quite specified what this mu of x is. Although, you know, you can kind of imply that this is our integrating factor, right? What if we use those two highlighted red parts to solve for what our integrating factor is? Okay. So let's do that. So let's take both parts that are highlighted in red, set them equal to each other, and what you're going to see is that we actually have an expression to solve for mu of x. Okay. Okay, so we have d mu dx is equal to p of x times mu of x. Okay. So if this equation is satisfied, then you know we can get our original equation into a you know, an integrable form. Okay. So let's take this and let's solve this for mu of x. Okay. So this is actually something that we can do. In fact, you know, we actually just did two examples of this because remember, P of X is something that's given to you in the problem. So that's P of X is something that's known to you. Okay? And so we have du dx is equal to P of X times mu of X. Right? This looks a lot like a separable equation. We're solving one ODE to solve another ODE. So, you know, I when I was like 12 years old, I think the show ran for a while. There was a show on MTV called Pimp My Ride with Exhibit. So it's like, yo, dog, I heard you love ODE. So we put an ODE in your ODE. So you can solve two ODEs at once. It's kind of the same thing. You don't have to solve this OD every time because it eventually just becomes a formula that you plug into, but this is kind of the motivation of that. So let's solve this really quickly. This will be the last thing that we do. I'm gonna give you the expression for the integrating factor, and then we'll pick it up on Tuesday. Okay. So let's solve this by separation of variables. So let's take this mu of x, let's divide it by both sides. Okay, so we have 1 divided by mu of x times d mu, and d mu dx is equal to p of x. Okay. Let's integrate both sides. I'm a war criminal. Move the dx over. Okay. So we have integral of 1 over mu d mu. That's going to be natural logarithm of d mu is equal to integral of p of x dx. Okay. Now p of x normally is given to you, but you know in this form we don't know what it is just yet. So I'm just going to leave it as a generic integral p of x dx. Okay. In this case, you know, I know we have indefinite integrals here, but you know, we're not actually solving this equation. We're just using it as a tool to solve our original one. So we actually don't need an arbitrary constant here. Okay. Just like we did with the second example, we're going to exponentiate both sides. Okay. And so we have mu of x is equal to e to the integral p of x dx. And this right here, this is our formula for the integrating factor. For linear All right, any questions on how we got to this expression here? Okay, all right, so we'll leave it off here for today. And so on Tuesday, go ahead and finish up this derivation. I'll show you the equation. We'll do a couple of examples so you can see how this is done. And then we'll move on to second order equation. So thank you guys for coming today. I hope you guys have a good rest of your evening. And hope you guys have a good weekend. I will see you guys on Tuesday.
It's very
Yeah.
Just a quick question.
Sure.
Like, when you wrote the A, does it matter? Like, what if I just kept it as like a C?
That's fine.
That's fine.
Yeah, whatever your favorite letter is.
Okay. It's because like I think our or my health professor was like there's a so
Yeah.
just
Yeah, that's
Okay.
fine. You can keep it as e to the c. So I prefer to keep it a just to make it same thing. So yeah, whatever works best for you. In the end, it becomes a sum.
Sounds like I